All right. My name is Mr. Kalman, and today we're going to be going over what are the real life applications of the mole. In this case, we're going to be focusing a lot on mole problems and converting moles to grams and things like Avogadro's number. So one handy thing you might want to pause this video for a second and grab or open up is a periodic table. And you also might want to have a calculator handy. If you don't have a calculator on you, you can use if you have a phone, your phone calculator might work. But also Google has a decent scientific calculator, so you can just go to Google and type in like scientific calculator, and you'll find it. It'll just kind of appear. So that way you can kind of follow along as I'm going through these notes. So the first thing we're going to be talking about today is calculations with moles. This is going to be converting moles to grams. So how many grams of lithium are in 3.5 moles of lithium? So first we're going to have our dimensional analysis table. We're then going to start with our given. Our given is right here with moles. So we have our given right here. And then we're going to look at our what we're trying to find, which is going to be how many grams of lithium there are. So we're going from first of what we're given, which is moles, and we're going to try to figure out the number of grams. So we're going to write our units on the right side here. So this is grams of lithium. Next thing we're going to do is have to make a conversion factor. So we're going to use our periodic table. You can find lithium on yours, or you can use the one we have up here. And you're going to notice that it has 6.94 grams of lithium per 1 mole. So it's going to look something like this. We're then going to cross out our same units. And then what you're going to end up doing is the way these work, and I think most people have this by now, but just kind of getting you an idea, is the top parts you're going to multiply. So you're going to, anything that's where the lines are, you're going to multiply, and anything that is underneath is going to be a divide. And so in this case, we're going to multiply 3.5 times 6.94. And that's going to give us our answer divided by 1 in this case. So what we're going to end up with is 24.29 grams of lithium. So our next section we're going to be talking about is converting grams to moles, and this way we're going the opposite direction. So we're going to have how many moles of lithium are there in 18.2 grams of lithium. So in this case, we have our starting units as grams. So we have our given, which would be grams here. And then we're going to have what we want to find, which is going to be moles. Oops, sorry, wrong color. Let's pick again. So we're going to find our moles of lithium, which should appear over here. Next thing we're going to do is we're going to have our conversion factor. We're going to use our molar mass, and we know that 1 mole is equal to 6.94 grams of lithium. In this case, we're trying to get rid of grams, so we want to put our grams on top and the bottom so that they cancel out. And then we multiply everything on top and we divide everything on the bottom. And in this case, we're just going to divide 18.2 divided by 6.94. Put that in your calculator and you get a 2.62 moles of lithium. This is kind of a little handy chart that might take a little bit to get, but once you get it, it's really useful. Basically, what this is showing is that the mole is the center of all of this. And so these are all conversion factors that go through the mole. So if you want to know if you are given the number of atoms or molecules, and you want to find out how many moles that is, you can use the conversion factor of 6.02 times 10 to the 23rd is equivalent to 1 mole. This is also the same for liters or volume. So 22.4 liters is equal to 1 mole. And the bottom part shows grams, and it shows how many grams are equal to 1 mole. And this is dependent on the periodic table, depends on the molar mass. So that last time we had lithium, which was 6.94. I had double checks. I don't have it memorized yet. Not that great. So essentially, this is just kind of a way for you to be able to quickly look at these conversions and kind of have it on hand. We're now going to move into something called scientific notation, mainly because we want to make sure you understand what Avogadro's number is and how this is working. So in this case, we have a few different parts of scientific notation. We have the coefficient. This coefficient has to be greater than 1 and less than 10. So in this case, we have 6.02. If it was 60, you would always put the decimal where the 6 is. So if this was 602, the decimal is always going to go here because that coefficient always is going to be greater than 1 and less than 10. The base, in this case, it's always 10. So luckily for us, we're using base 10 and not something else that you might do in other math classes like other bases. So we're not going to have to worry about those other ones. So it's always base 10. It's always just going to be times 10 to the whatever power, and the exponent. Now the exponent is just going to tell you the number of decimal places the decimal is moved. Positive exponents are used for larger numbers, and negative exponents are used for smaller numbers. A kind of general rule of thumb is if you're given a scientific notation and it's a positive number, that decimal is going to move to the right. And then if it is a negative number, that decimal is going to move to the left. So if you're given the scientific notation, something like this, an easy way to kind of think of this is that positive numbers are going to move the decimal to the right, and negative numbers are going to move them to the left. Remember, positive exponent is used for a larger number than 1, while negative 1 is used for smaller than 1. So just another thing to realize as well. So using a scientific calculator notation with a calculator, obviously it's a little bit harder to do this without one. For some of these you can, but really a calculator is really used for this. In most calculators, they have a key that's either going to be labeled EE or EXP that is used the following way. So if we're going to look at 6.02 times 10 to the 23rd, this EE is going to stand in for basically times 10 to the whatever power. So in this case, we have EE is going to basically equal that times 10 to that. So it's going to basically be that. And that's kind of what it looks like on the calculator. In this case, they will probably, and the same thing for EXP, it would be the same way you enter in the calculator. Although when you hit enter on it, it's going to give you a number that might look a little different. In this case, that E is going to equal to that times 10 to the power of. So in other words, this is going to be kind of a key you're going to look for. So that's going to equal the same as this single E here, or the E plus is going to represent the same thing, or it might even just have the actual exponent, which would be interesting as well. It depends on the calculator. So you're going to have to play around with the calculator you have, just kind of get used to it. I suggest starting with something really simple that you know the answer to. So if you do something like 1 times 10 to the second power, you know that's going to equal 100. So 1 times 10 squared is 100. So that way you can kind of play around with the calculator and you know what the answer is supposed to look like. You can also just do this the same type of way with just so you get an idea of how you're entering it. And that's kind of the biggest point. In Google, again, if you just search online free scientific calculator, it should pop up with a good calculator to use. That EXP button, in case you're wondering where it is right over there. But that's what you can use when you're entering. Okay, so here's a couple of reasons why we use scientific notation. So every field will use scientific notation at some point. Biology, chemistry, physics, they all use it because science tends to work with sometimes really, really large numbers and very, 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 very small numbers as well. So a couple examples here are massive electron. We have the massive electron is really, really tiny. It has 24 zeros basically from the decimal point. And in this case, we have the mass of the Earth, which is really, really large in grams. And so that would mean it's going to have a large number and a big exponent. If you want, you can count all the zeros, and basically we're going to go over how this works in a second. So we're going to convert these to scientific notation. And a couple of tricks we can do with this is we're going to be counting over the number of decimal places. So the first way I generally start this is I actually just write out, if I'm going to convert a number to scientific notation, I start out with 2.50, and then I just write times 10. And then in this case, I'll be 100% honest, I don't know if it actually lets me do exponents on this. It does not. So I'm going to use a, this is to the power of. And so that little caret there basically means power of, and then I'm just going to put the number there when I get to it. So I'm going to count now how many decimal places this is going to move over. And a couple things to kind of realize is if this is a small number, it's going to be a negative number. And if it is a positive number, it's going to be a big number or not a decimal. So we're going to count the number of zeros. So we have a 1, 2, and 3. So this is going to end up being to the power of -3. So this is basically going to be times 10 to the power of -3. And it looks something like that. And I could have just gotten rid of the caret if I can move this. But you get the idea here. So let's do this next one. And I start with the same process. I just write the 4D9 or 4.95. And then I also going to write multiplied by 10. And then I'm going to figure out how many the power is going to be. And we have to first find our decimal point. So our decimal point in this case is here. So we're going to have the power of 1, 2, 3, and 4. And I know it's a little hard when I'm doing it on a mouse like this, but you're basically just counting how many over it works. So this is going to be the power of 10 to the 4th power. So I write my 4 right here. Now just a little math trivia, and just to kind of show you and remind a lot of you like how this works mathematically. If you have something like this where it's 10 to the power of 1, that basically is going to equal, so I'm just going to put an equal sign, and that basically is going to equal this. It's going to equal 10, and then you're basically going to have it's going to basically equal 10 over 1. Ten to the -1, so 10 to the power of -1, on the other hand, is going to be the opposite. It's going to equal, and it's going to equal 1 divided by 10. So that's how this is kind of working. So in case you weren't sure how this works and you wanted to see how it works, that's how these powers are working. It's just kind of a reminder of it. Okay, so again, we're going to convert the following to standard notation. What I generally do here is, in this case, the way this text box works, I'm not going to write it that way. But generally what I usually do is I'll end up writing something like this. I'll do 1, 3, 0, and then I'm going to add all the zeros in front of it that I need to count before it. So basically what I end up doing is I take my decimal point, and it starts here. And what I'm going to end up doing is I'm going to be moving it over 5 spaces. And a way to remember this is that because the negative sign is on the left side, I'm going to move that decimal point to the left. So I'm going to take this decimal point, and I might have to redo this just because how this works on my annotation. But I'm basically just going to have 5 times I'm going to move it over. So I'm going to move it 1, make a 0 here, 2, 3, 4, and 5. And that's how many zeros I'm going to put in front of this. So if I make my text box here, I would basically add a 0 and then another 0. So you can kind of see this. 0, 0, and then I know it looks a little weird. And then I would have a 1, 3, 0. So we can now collapse this just to make it easier. When you do this on paper, it works a lot nicer. And then I put my decimal point, and because it always looks kind of weird without a 0 in front, I always like to do this. So this is what your ending result's going to be. And that's basically where you're going to have your, and let's erase this now. And so now that's what we're going to have. So in the other way, our other example here is 3.5 multiplied times 10 to the 5th power. So we're going to do the same thing. Generally, what I do here is we're going to move it 5 decimal places over. So this is going to move 5 different decimal places to the right because there's no negative sign. It's going to be a bigger number. So we're going to move it 1, 2, 3, 4, 5. What that means here is I'm going to have a 0 here. Oh, it's a terrible 0. Sorry, guys. I was trying a different way. So we're going to have a 0. We're going to have a 0 here, another 0 here, and another 0 here, and another 0. So at the end, our result's going to be 5, and then 1, 2, 3, 4 zeros. And if you really want to put the comma because you like to be able to separate it, you can. And that's what you get, 350,000. So I'll erase this now. And that's how you convert to scientific notation. And let's clear box. Using Avogadro's number, how many atoms of lithium are in 3.5 moles of lithium? So now we're going to use that large number and practice using it in the calculator and getting used to writing in that scientific notation. So again, what we're going to do is we're going to look at what we're given. We're given 0.5 moles. So we're given that 3.5 moles, which is going to show up right here. We're then trying to find our number of atoms. And so that's going to show up over here. So we have 3.5 moles. And we have atoms. Nope, I guessed a little bit wrong, but it's roughly the same spot. So we're going to have a number of atoms of lithium. We know that 1 mole of anything is going to be 6.02 times 10 to the 23rd of it. So we're going to have converted to atoms. So you're now going to multiply in your calculator 3.5 moles multiplied by 6.02 times 10 to the 23rd. Remember, that might be that EE key or the EXP key. To the 23rd, and you're going to end up crossing out your moles, and we're going to get a number like this, 2.107 times 10 to the 24th power. And it moved out a little way, but we're going to talk about something called standard molar volume. Equal volumes of all gases at the same temperature and pressure contain the same number of molecules. This is one of the things that Avogadro figured out, and it's really kind of cool. So basically what this is saying is that if I have a certain volume of something, it's at the same temperature and pressure. It doesn't matter what gas I have in there. If I have carbon dioxide, it's going to have the same number of molecules as long as everything else is the same. If it's oxygen, if it's nitrogen gas, if it's nitrous oxide, or any other gas like water vapor, it's all going to have the same number of molecules. And what we also have here is he also figured out, and we kind of standardized this. So at something called standard temperature and pressure, which you might remember from a while back, which is 0 degrees Celsius and 1 atmosphere. At these temperature and pressure, you're going to have 1 mole of gas will occupy about 22.4 liters in volume. So that's what the conversion is, and that's where we're getting this. That's how we get the conversion. So how many moles of hydrogen are there in 100 liters of, how many moles of hydrogen are there in 100 liters of hydrogen at standard temperature and pressure? So we're given 100 liters, and then we are looking for the number of moles, so moles of hydrogen here. And so in this case, we're gonna take 22.4 liters, and that's gonna equal to 1 mole. And we're gonna cross out those liters, and we're gonna convert it, and it's gonna multiply everything on the top and divide it by the bottom, and we're gonna get about 4.46 moles. So there's 4.46 moles of hydrogen gas in whatever, in that 100-liter container. As long as it says how many, and we're going to do the opposite way. How many liters are occupied by 3 moles of oxygen gas, standard temperature and pressure? So we have 3 moles, that's our given. We're trying to find liters, and we know our conversion is going to be 1 mole, and it's going to go on the bottom because we're going to get rid of this unit, is equal to 22.4 liters. So we're going to cross out that mole, multiply everything on top, and we get 67.2 liters. So these are something called, what we've been doing and using this entire time is something called conversion factors. They come from equivalent relationships between 2 units or an equality. And when you use conversion factors, they're written in the fraction form or the picket fences. Either way is fine. Generally, I prefer the picket fences. It just kind of separates things nicely. Some of you may like, and we're going to show the other way, the fraction form as well. So you'll see that fraction form, whereas before we were doing that picket fence style here. So just a kind of reminder, what this means is when if you have an equivalent unit, so if you can picture a meter stick, that's what this is representing here. 1 meter or 1 meter stick is equal to in length as 1,000 millimeters. This makes a lot of sense. So you can write our conversion factor in 2 different ways. We can write 1 meter over 1,000 millimeters, or you can flip it and make 1,000 millimeters over 1 meter. This works because 1 meter is 1,000 millimeters. So if you divide something by itself, it equals 1. So it doesn't matter how you flip it. This is basically saying 1,000 millimeters over 1 meter. That's how this kind of works. Same thing with inches. So you have 12 inches in a foot. It doesn't matter because this equals the same thing. It's the same thing that happens with our molar mass. Our molar mass is that number that you find on the periodic table. 1 mole is equal to that molar mass, whatever it is. If it's hydrogen, it's 1.01. So 1 mole is equal to 1.01 grams of hydrogen, for example. Or oxygen is 16, etc. In this case, all gases are equal to 22.4 liters, as long as it's at standard temperature and pressure for 1 mole. And the last thing is those particle number, which is 1 mole is equal to 6.02 times 10 to the 23rd. So again, PA, that's just meaning particle. This could be atoms, particles, molecules, etc. So it's just a number of things. Think of it like a dozen. So, all right. So we're gonna start doing 2-step dimensional analysis. I know a lot of people before struggle to see the importance of doing this, either fractions based or the picket fences. And that's because when you're doing one conversion, a lot of people feel comfortable just multiplying by the right way or dividing by the right way. But in this case, when we use units you're not familiar with, like moles, or we do multiple steps, it's really a lot easier just for your brain to process using this dimensional analysis process. So an example of this, and this is not going to be moles, but it's just a way to show the 2-step. We have 2.5 meters, and we want to convert it into inches. So we're given 2.5 meters, and we want to convert this into inches. So we have our meters here. We want to convert this into inches. And the first step we're doing is we're getting rid of that meter. We have a conversion factor that says 100 centimeters equals 1 meter. So we want to get rid of this meters here. So we put this on the bottom. So that's our first conversion factor. The second one is we want to get rid of that centimeters because we're trying to find inches. And we don't have inches yet or anywhere here. So we want to get to inches. So we're going to now use our second conversion factor and put our centimeters on the bottom. so that they cancel out because centimeters over centimeters cancels out. And then you multiply everything on top. So 2.5 multiplied by 100 divided by 2.54, and that's going to give us 98.4. Again, just remembering to cross out our, let's use peak and cross out our units so that you can kind of see how this works. So the meters are crossing out. And you're also crossing out those centimeters, those different units. So what you're left with now is what we wanted all along, which is inches. And this is kind of one of those ways to keep track. All right, so a couple of practice problems here. I'm not going to go through all of these. I'm just going to do one or two of them just so you kind of get some practice on this. So we're going to convert 2 feet into meters. So the way I'm going to do this is I generally prefer using that picket fence style. So I'm going to, let me not use green. Let's make this. So I'm going to draw out here a big line. We're going to look at this problem and it says convert 2 feet into meters. So we're going to start with our 2 feet. And we want to convert this into meters. So that's our given. So we're going to start, and I'm going to use this in red so you can kind of see it, is we have 2 feet. And we're going to convert this into meters. So we want to end up with that unit meters. So while we are doing this, have your calculator ready so you can kind of practice it. And then the next step we're going to do is, because we have, there's no direct conversion from feet to meters. We have a conversion from, you're going to actually have to look at a couple things to see this. One of the things that's not on here is feet to inches, which most of you should know. So the first thing you have to do is get rid of that feet, and then it will convert to inches. So we're going to have a line here, and we want to get rid of those feet. So we know that for every 1 foot, wrong color, sorry. For every 1 foot, there is going to be 12 inches. So in this case, I'm going to pick a different color here. And I'm going to say this is 1 foot is equal to 12 inches. So I'm just going to put IN. In this case, inches are not meters, so we have to continue on and get rid of the next one. So let's make another picket fence line. And now we have to look at our conversion factor, and we're going to get rid of inches to centimeters. So we have 1 inch is equal to, oops, wrong color. And now I'll use my blue up here. And this is going to be equal to 2.54 centimeters. We then need to make another line because we're not finished yet, because centimeters is not a meter. And now we're going to get rid of that centimeter. So we're going to take that conversion, which is right here. We have 100 centimeters. And we're going to, which is equal to, and now we finally get to that nice green answer, 1 meter. And now again, what you're going to be doing here is you're going to be taking everything in your calculator, 2 times 12 times 2.54, and divide that by 100. And that's going to give you your answer. Now, I want you to do this on your own so you can practice in the calculator. I'm just going to help you with the setup. That's all this practice is for. So the way to check to see if this is right is you want to make sure you're crossing out those units properly. So we're going to have feet here and feet here. Inches is going to be here and inches are going to be here, so they're crossed out. Centimeters and centimeters, and we're finally left with that unit we wanted, which was meters and meters. All right. So moles and dimensional analysis. So in this case, it's the same type of principle as what we were doing before with the feet and inches, etc. Except this time we're converting moles to either Avogadro's number. So in that case, it can be either this or this. So you can have 1 mole over 6.02 times 10 to the 23rd, or you can have 6.02 times 10 to the 23rd over 1 mole. Again, formula mass, which is the same thing as basically saying molar mass in this context. So in that case, we have, let's say it is water, for example, which is 18.02. And the formula mass will go on top. In this case, we have 1, and then now we're going to have our liters at STP. So 1 mole of gas is equal to 22.4 liters. The other conversion factor is 22.4 liters over 1 mole. Last one is we have 1 mole of water, H2O, is equal to 18.02 grams. This is that molar mass. And basically, the way we got that 18.02 is if you can watch the video from last week from Ms. Rainieri, she went over this as well. And it's basically you take that 18.02 grams, and we got that because 1 oxygen is equal to 16 grams on the periodic table, molar mass, and hydrogen's each worth 1.01, so there's 2 of them. You add that all together, it gets 18.02. So now what we're going to be doing is we're going to be converting a couple of these in multiple steps. So suppose you're given 70 grams of salt and asked to calculate the number of particles in the sample. How would we do this? Well, the first thing you're going to be doing is we have to figure out the formula of the compound. So in this case, we have Na, +1, NCl, -1, charge, and luckily they cancel out, so it's really simple. It's NaCl. We're going to find the molar mass. You're going to use your periodic table. We've done this for you, but if you look on it, we have the molar mass of sodium being 23 grams, and the molar mass for chlorine being 35.5 grams. We add them together and we get a molar mass of 58.5 grams. Now what we're going to be doing here is we're going to be using dimensional analysis. We are given, and I've been using, there we go. We are given 70 grams of NaCl, or salt, and we're trying to find, in this case, the number of particles. So we have that number of particles we're trying to find. So that's going to end up over here. So first thing we have to do is we have to convert to moles. So we have 70 grams of sodium chloride. We're going to get rid of that gram units and cross it out, and then have our moles here. We're then going to multiply it by Avogadro's number over 1 mole, because we want to cancel out that mole here. And this is going to be multiplied all together on your calculator. So you multiply 70.0 grams times 6.02 times 10 to the 23rd units times 1. And then you're going to divide that by 58.8 grams. This is going to end up with something in your calculator like 7.20 times 10 to the 23rd. This is our given unit, our conversion factors here, and our answer is over here. Crossing out our units to double check our work. It doesn't matter how you do this, if you want to do this as you go along or at the end, either way is fine. And you're just checking to make sure the units that you end up with, this should really say particles, not units. Units basically is just a stand-in for atoms, molecules, or particles. In this case, we wanted particles, it's the same. So you just write particles instead. And then we're good, we have the right unit here. And let me clear off all the tries. So when we're doing these problems, whenever you're doing conversions using dimensional analysis, you always put your given amount of units and your units. So this is kind of the starting point. It's what I've been saying all through this. 1 mole always shows up in your conversion factor. If you're given mass or particles, you must first convert to moles. So in this case, this is where this graphic comes in handy. So everything has to go through moles if you want to get from one of these to the other. So if you have, let's say we're starting with grams, and you want to get to liters, you can't just go from grams directly to liters. You have to go from grams, convert it to moles using that molar mass on the periodic table. And then from there, you can then convert a mole to a liter. So this is why it's called a two-step. One step to go from grams to moles, the second step to go from moles to liters. If you want to go and understand how many liters of, or let me take it back. If you wanted to figure out how many atoms are in a 2-liter bottle, then you'd have to start with 2 liters, convert it to moles, and convert it to atoms. You can find out how many oxygen molecules could theoretically be in a 2-liter bottle of soda. So here's a couple of example problems that we have. So suppose we were given 8.63 grams of sulfur and are asked to calculate the number of sulfur atoms in the sample. And it looks like, oops, this is not actually here. So let's do a couple of things if we are stuck like this and we need to actually convert through it. So the first thing we need to do is we need to figure out our givens and so we're given 8.63 grams of sulfur, and we're asked to calculate the number of, so what we want to find is the number of sulfur atoms. So I'm going to draw my dimensional analysis table here. So I am starting with and I'm going to use red here. So I am starting with 8.63 grams. And what I'm trying to get to is at the end, I want to find sulfur atoms. So I want to find the atoms of sulfur, or just sulfur, which is S. So what we're going to be having to do here is a couple things. The first thing we need to figure out is we want to get rid of, and this is where we're using that. So if we go back to our handy dandy chart, oops, it's in the way, sorry. But if we go back to this handy chart, we have a grams. We need to use our molar mass, we need a periodic table, and convert to moles. Then we're going to convert from moles all the way so we have grams, we want to use a periodic table, convert the molar mass to moles. Then we want to take our moles and convert our moles to atoms. So that's kind of how this works. Next one, let's redo what I had so far. All right, so the next step I'm going to have to do in this case is we need a periodic table. So let's say I don't have one on me. What I can do is you can look online, and we gave you a periodic table to use. There's also a periodic table that I like to use every once in a while as well, and it's just P table for a dynamic periodic table. And I'm just going to use to get that 32.06 grams for the sulfur. So I'm going to take that 32.06. And I know that we have 32.06. This should be red because it's going to be grams for every 1 mole. And I'm going to use a different color. Let's use blue. So for every 1 mole. And then we're going to have to check to see if this is what we want. Is this number of sulfur atoms? No, our units are moles. We're getting rid of our grams are now gone, so we don't have to worry about grams. And I always do this check. Is the unit I currently have what I want at the end? It's not, so I have to keep going. So I have to figure out, I have to take moles and I have to convert this to atoms. Buckley is a nice way of doing this. We know that for every 1 mole, we have the number of particles is 6.02 times 10, and I do it this way because it's kind of weird on this 23rd. So then what you're going to do is multiply the top. So we're going to, well, oops, I jumped the gun a little bit. First, we need to cross out our units to make sure our units are the right. And again, this is going to be the number of atoms And so now we can check our units. We have grams are canceled out, moles are canceled out, and we're left with atoms. And that's what we wanted. We wanted atoms. So now we're ready to put it in the calculator. So now you're going to take your original starting, 8.63, multiply it by 6.02 times 10 to the 23rd, and then divide that number, whatever you get, by 32.06. What you should get is, let me clear out my drawing, 1.620 times 10 to the 23rd sulfur atoms. So you should get this number in your calculator, or very close to it, because sometimes they round a little bit. That's what you should be getting. All right, so in this case, you have, you should not practice on your own. You have a sample of copper 2 nitrate containing 3.48 times 10 to the 24th particles, and are asked to calculate the mass of the sample. So a couple steps you're going to have to do here to get this is the first thing is you're going to actually have to figure out what copper 2 nitrate is. Remember that copper 2, this means that it's going to be a copper with a charge of +2. You're then going to have your nitrates. You're going to have to look at a polyatomic sheet. If you don't have a polyatomic sheet and you don't have your periodic table, you can always just look this up and look up a polyatomic table in Google, and it should find them for you. So you can look up polyatomic ions, and there should be, and usually I just do a chart or list, and the first one coming up should come up pretty much similar. And then we're gonna we can quickly search nitrate, which is NO3 -1. So let's copy this so we can paste it really easily when I'm doing these. And the main reason why I'm showing this is in case you're home by yourself and you're like, wait a minute, I don't have my periodic table, I don't see the polyatomics, and I just want to make sure you feel okay. So we have this, which it's going to be NO3, then it's got a charge of -1, or just negative. And so, oops, that looks a little weird. Let's, sorry. Okay, so let's undo that negative sign there. I don't like it there. So let's put that negative sign right here so you can actually see it. It just wasn't showing up right. So let me do that drop and swap. In this case, we're gonna have 2 nitrates molecules, and we're gonna have 1 copper. So your copper 2 nitrate is gonna look like this. You're gonna have Cu, so we're gonna have 1 copper. Then you're gonna have that parentheses NO3 parentheses. Let's actually put the 3's where they should be. So let's put the 3's below like they should be, like a subscript. Unfortunately, this doesn't allow me to subscript, so I'm just kind of doing the best I can with it. Yeah, I can shrink it to be better. So it's gonna look something like this. NO3 parentheses 3. And that's what copper nitrate is. So then what you're going to do is have to calculate the mass of these. You're going to look up on your periodic table the mass of copper, the mass of nitrogen times 3, the mass of oxygen times 9. Add that all together, you're going to get a molar mass. You're going to start with particles, divide by that. So you can kind of set this up in a way of, so what you can do is we can set this up to where, sorry, you can use your picket fences, and you can start with those number of particles. So we can start with our .48 times 10 to the 24th power. I'm going to use that little caret just to keep it a little bit quicker. So we're going to start with those particles, and this is going to be particles as our unit, or PA short, and that way I can just move it and we can keep it there. So we have our particles. We want to get rid of particles, so we do know that 1 mole, let's make mole different color. Let's make this nice and blue. 1 mole is equal to, and that's going to be those particles. So it's 6.02, it's Avogadro's number, times 10 to the, I'm going to use that little caret again, 23rd. We're then going to separate this out. And that's going to be particles here as well. So just kind of realize that this number is going to be the same. So if I do that here, just write PA again to indicate the unit. Next thing we have is we're going to look at moles. We're not looking for moles, we're looking for mass. So what you're going to do is the next step is going to be putting 1 mole on the bottom. So this is going to be that blue color. So 1 mole. And at the top, we're going to end up with whatever the mass is. So if you add this all up, you're going to get a mass, and it's going to be the actual molar, let's change this to green, molar mass of, and that's going to be of copper nitrate, which is above that Cu NO3 parentheses 3. And then you're actually done. You just need to now put it in your calculator. So you're going to take this 3.4 times 10 to the 24th, multiply it by that molar mass, divide it by 6.02 times 10 to the 23rd, and you're going to get your answer, which should be somewhere close to, because again, sometimes rounding happens, 1,000 grams of copper nitrate. This case, we actually have this here. I didn't want to look up and take the time, but if you practice the other one, it would work. So in this case, you have 17.9 moles of water. And what is the mass and number of molecules for water? So it's asking for 2 different things here. So you're starting with moles, and we're converting this to mass. And then this is basically 2 problems within 1. So you're going to have 2 different problems, and there's not really much space on this to do this, but basically you're going to only have a 1 conversion for each. So the first one you're going to set up, and it's going to be 17.90 moles of water. And you're going to have that same starting on the other side too, but I'm going to worry about that later. I'm going to try to find mass the first time. So the first one I'm going for in this case, so I used the wrong color, didn't I? We're given this number here. There we go. And we're given that, so it's going to be 17.90 moles. So what we need to do here is to find mass, which is what we're going to try to find on this one. We're going to try to find mass. Mass is going to be in grams. No, bad color. So mass is here. So we're going to basically find that molar mass, which we're given that conversion factor here, which is 18.02 1 mole, because we want to cancel out our moles. I thought it was on top for a second. It wasn't. And then we're going to multiply this by 18.02 grams. And that's going to give us the right amount. So you multiply these together, and you're going to end up with your grams. So the setup on the other side is very similar. What you're basically going to have is you're going to start. So for the second one, when we're trying to find the number of molecules, so let's just make this blue, because that way we can kind of see it as a little different. So I'm going to erase these numbers. But the cool thing is we do know one really easy way. This is literally just going to be the same setup, except for this time it's going to be multiplied by Avogadro's number. And this is molecules. And then that's going to get your answer, which is going to be 17.90 multiplied by it. And that's basically all there is to this one. So this one you'd have two answers. So these are all the same types of practice that you should be doing to see how this goes. And the last thing is just kind of a reminder for everything. So remember that molecular and formula mass measure the masses of tiny particles too small to see. The unit for these measurements are AMUs, atomic mass units. Molar masses are going to be the mass of 602 sextillion atoms, or 6.02 times 10 to the 23rd. And the unit for molar mass is going to be grams. Elements are composed of atoms, so just kind of remember this. So if it's an element by itself, it has a number of atoms. If it's asking for a molecule and it's asking for the number of molecules in it, it's going to be a molecule, things like that. And the last part of slide we have today before I finish is given the mass, given mass is the mass you're given. It can be any amount. Molar mass will always be 1 mole of substance. It'll always be looked at on the periodic table. It's calculated by adding up all the atoms / ions, which should have the same mass, and are expressed in grams. In this case, the ions, because the electrons are such a small mass that we just basically count them as negligible. Because you either begin with moles or convert directly to moles, 1 mole shows up in every conversion factor. So when you're doing these problems and you're doing these practice problems, you should have moles somewhere in here. So just to give an example of another setup of these, if we want to do 20 grams of moles into moles of water, we're going to start, and I'm just going to kind of do this a little quickly, so I'm not going to go as slow as I was before. So we're basically going to, actually, hold on. So we're going to take that initial starting grams. So we have 20 grams of water. Water is got a molar mass of 18.02, 16. And this is going to be grams. And this is going to be for 1 mole. So 1 mole. And this will convert directly into moles. So you're going to have a mole in every single one of these. The next one is basically very similar. So it's asking you to start from molecules and going to grams. So I'm going to take my, this is actually going to be a 2-step. So I'm going to, well, I do not like that one. I know my lines have not been perfectly straight all night, but I don't really like where that one's at. So we're going to start here, and we're going to start with 6.02 to the 23rd. This is going to be those molecules, and I know it's going to be a little bit covered on here, just because it's not like a whiteboard I can write on. So just kind of bear with it. And then we're going to get rid of that using a conversion factor. So in this case, it is also 6.02 times 10 to the 23rd. And that's because that's the conversion actually for 1 mole, which 1 mole goes here. I was just looking at the problem going, this one should be really straightforward. We're going to then have 1 mole of water, and that's going to equal the grams, which is at 18 of water, which is that formula mass or molar mass. And the cool thing about this problem is we know the answer. It is literally going to be 18.02 because you cross out these. So in this case, we cross out our units and we're left with grams, and that's going to give us our final product. These same ones, you do the same kind of setups. You're just starting with moles, ending with it. And so these are just going to be some practices for you to do. Other than that, hope you have a fantastic time of day it is, whether it's morning, evening, night, or middle of the day. And have a fantastic time.